Welcome to the next video in the mathematical logic series. We're still talking about the syntax of propositional logic. We're going to see a first proof. Here we're going to characterize the set of sentences that, as we have constructed it in the previous video, as a kind of bottom-up construction. We're going to see that there's also a top-down construction. And then we're going to claim and prove that the two constructions get you the same set of sentences. Just to sort of explain this characterization, when we define the set of sentences, we started from sent 0, which is like an underestimate on the set of all sentences, because we only have a fairly small subset, right? We have only the sentence symbols, sent 0. From that, we can build up the next more complex collection of sentences, sent 1. And then from sent 1, we can build up sent 2, and so on. At any stage, it is a strict subset of the set of all sentences, and we keep getting more and more sentences as we go to the next sent n. If we then union them, in the limit, so to speak, we get all of the sentences. So that's a bottom-up construction, right? We start from too small and we build up and up until we reach the right set. So let's now see, or at least start thinking about, a top-down construction where we start from too much. Now in this construction, because we're going to start from too much, well, what that must mean if this is more than the set of sentences is that we're going to have sets that have expressions which are not even sentences. What that really is going to mean, in a sense, is that they are meaningless expressions, or at least expressions that we will never try to give meaning to. So for instance, right, one such set which has all of the sentences in it, but then more, right, even more than just the set of sentences, is the set of all L expressions. So that's a wild overestimate, right? It's just got everything in it. It's much too big. But what we're going to do is find a way to kind of carve it down until we remove all of the things that we don't, ultimately want to call sentences. So, to help us to define exactly how we do this, we're going to define this notion of an inductive set, or for my purposes here, more particularly, we're going to define what it is if X is a set of L expressions, Y is another set of L expressions, what it is for X to be inductive for Y. It's going to have two conditions. First, Y must be a subset of X. Second, X must be closed under all of the connectives. And what that means, right, in case this takes a little bit of explaining, is imagine that you select any E in X, the negation E must also be in X, so that X is closed under forming negations. And likewise with the other connectives, although this time we need to talk about an E and an F, right? So if you take an E and an F in X, form any binary connective on those, then that must also already be in X, right? That's closure under the formation of those binary connectives. So effectively, X is inductive for Y if X contains Y and is closed under the formation of any of the connectives. So that's what it is for X to be inductive for Y. Let's do a few quick exercises to get sort of warmed up to this definition. Let's take just about almost the minimal example we could consider, which is that you've got X and Y, both just single element sets, in particular this set of P1. So the left one is our X, right? The first one is X and the second one is Y. Does this satisfy the definition of X being inductive for Y? Well, certainly the first clause is met trivially, because any set is a subset of itself. How about the second condition? Well, no, right? Somewhat clearly, this is not closed, for instance, under the formation of negations. It's also not closed under any other of the connectives. But, you know, I can find an expression in X, right, namely P1, such that its negation is not in X. And so it's not inductive for Y, or this particular Y. Anyway. Now let's really take the minimal example, which is the empty set inductive for the empty set? Well, if you recall your set theory adequately, and I do strongly encourage you to pause the video, work this out for yourself. You'll learn this material much better than just listening to me go on, if you really sort of think independently. So anyway, pause it and then see what the answer is. But clearly the first condition is met because the empty set is a subset of any set. You may want to recall that that is true due to vacuous quantification, which is to say, we consider take any element in the empty set, is it in, in this case, is it in the empty set? Well, since there isn't an element in the empty set to take, we regard that as vacuously true, and we call this vacuous quantification, right? Whenever you make a sort of a for all claim ranging over the empty set, it's just, right, no matter what comes after that, we just say that this is vacuously true. It has to be a for all, and then underneath that it has to be a conditional, but whatever, right? I'm going to assume that you have studied the relevant material to kind of just need a reminder of vacuous quantification without necessarily going into the details and the reasons. So anyway, the empty set is a subset of every set due to vacuous quantification. Likewise, the second condition, right, the closure properties hold, again, due to vacuous quantification, right? We'll take an expression E that is in the empty set, but there isn't one, so due to vacuous quantification, the sentences all come out true. So yes, indeed, the empty set is inductive for the empty set. Okay. Does there exist any finite set X which is inductive for this particular fixed choice of Y, the set P1? Can we find any X which is inductive, any finite X which is inductive for this Y? Well, intuitively, hopefully it's clear that the answer is no. And in particular, we could just focus on negation because negation, it's relatively easy to just use the unary operator when we can just talk about it. So let's think about closure under negation, right? If we take any set which is inductive for P1, it's going to have P1, and then it's going to have its negation, and then it's going to have the negation of the negation, and so on to infinity. So intuitively, the answer is no, that this should not be inductive for P1. To flesh that idea out just a little bit more fully, just to sort of convince you that the argument can be made rigorously, suppose for contradiction that such an X existed. Well, it cannot be the empty set because then it wouldn't satisfy the first condition that the Y must be a subset of X. So it has something in it. We could even particularly say it must have P1 in it. And it is a finite set. So let's just focus on negation again and say, look, since it is a finite set, and we could take every element and count up the number of negations in each expression. And then we could take the maximum over all of those numbers of negations for each expression. That maximum number must exist because it is non-empty and finite. And then due to this x having to be closed under the formation of negations, we can take an expression which has the maximum number of negations. And we know that x must have its negation, which has one more negation, which is to say x has an expression with more than the maximum number of negations. That's a contradiction, so x cannot exist. One more exercise, and this one really does lead into the next thing that we talk about, so this is not merely an exercise, this is actually going to do a little bit of work for us. Does there exist a set x which is inductive for every choice of y? I've mentioned a couple times now the set of all L expressions, and so hopefully that comes to mind. And that's the answer is yes, that x could be the set of all L expressions. And you can see that that meets the condition, satisfies the condition for being inductive for y. Okay, let's look at the first clause. Y is a subset of the set of all L expressions. Well, that's just trivially true because y is assumed to be some set of L expressions. Okay, how about the second condition, closure properties? Well, certainly, right, if you've already got everything, then if you take any element, E, right, take anything out of the set, call it E, take its negation, well, that's just another L expression and therefore is in the set of all L expressions. So the answer is yes with x set to the set of all expressions. And I mentioned the negation, but you could run through the same exercise doing it basically the same way for the other connectives. So now I can start describing what this overestimate picture is. It will help us to have this symbol for the set of all sets of expressions which are inductive for cent zero. We will take this gamma, right? This is the capital Greek letter gamma. A set will be one of these gammas if and only if gamma is inductive for cent zero. So cent zero is being fixed, right? Cent zero is the y, gamma is the x from before, and the y is being fixed as monotonously cent zero. And gamma is anything that is inductive for that. And the calligraphic I is the set of all gammas like that. Okay? So notice I is a set of sets of expressions, right? Gamma is a set of expressions. I, calligraphic I, is a set of sets of expressions. If necessary, take a moment to process that and be clear about that. Okay. By the way, right, based on the exercise that we did just a moment ago, I is not empty because it has the set of all possible expressions. Because we showed that the set of all L expressions is inductive for every set, and so in particular we can take it to be inductive for cent zero. So the set of all L expressions is inductive for cent zero and is one of the gammas. Just to give an instance, right, and that's just demonstrating that the calligraphic I is not empty. Finally, we can state and then prove the claim that, actually first, here's the construction, right? We now have the top-down construction. We intersect all of the gammas, right? Take every gamma in calligraphic I, take their intersection. That's the top-down construction. And we know you can kind of imagine that it starts from having all possible L expressions. But as we take intersections, we start chopping it down and chopping it down, right? And so in the theorem that we're going to prove in a minute, we're going to argue that it cuts it down just to the cent L. So we're going to claim that the set of sentences given by the bottom right, cent L, remember, was defined through the bottom-up construction. We're going to prove that it's equal to the top-down construction. This is going to be a subset proof in two directions, so we're going to start with the left, a subset of the right. This direction is going to be a fairly standard show that the thing in the left is on the right. Although in particular, the thing that's on the right is an intersection. Therefore, to show that the thing on the left is in that intersection, we really want to show that if you take, if you take any one of these gammas in I, that cent L is in gamma, right? That effectively is really just the definition of what it is to be in an intersection. So that's the first move that we're going to make, right? We're going to pick any particular gamma in I, and we're then going to try to argue that cent L is a subset of gamma. If we could do that, then it would, right, that is sufficient proof. In particular, before really getting to cent L, I'm just going to prove by induction that cent N is a subset of gamma for every choice of N. And then from that, right, once we have that, it'll just follow trivially, because cent L is the union over all cent N. It is trivial to show that from that, we get that cent L is a subset of gamma. Okay, for the base case of this proof by induction, we're going to try to show that cent 0 is a subset of gamma. But look, gamma was assumed, right, by its very definition to be inductive for cent 0. And the first clause of what that means is that cent 0 is a subset of gamma. So base case dealt with. Okay, for the inductive case, we'll assume for the inductive hypothesis that cent N is a subset of gamma. And we're going to try to prove that cent N plus 1 is also a subset of gamma. And we're going to prove that by basically cases in a minute. So, right, to prove this subset, right, we're trying to prove, based on all these assumptions so far, that cent N plus 1 is a subset of gamma. So I'm going to do a regular element chasing subset proof where I take an element from the left, call it phi, and prove that it's in gamma. So I'm trying to prove that phi is in gamma, the assumption that phi is in cent N plus 1. How am I going to prove that phi is in gamma? It's going to be a proof by cases, right? Recall that cent N plus 1 is defined as cent N union the negation of cent N union all possible binary connectives on cent N and cent N. So I basically got 3-ish cases depending on how you want to count. The first case is that phi is in cent N. But the inductive hypothesis already assumed that cent N is a subset of gamma, and I'm done. Let's move on to the next case. Suppose that phi is in the negation of cent N. Well, by definition of that, there exists some psi in cent N such that phi is negation psi. And that's just the definition of our notation here. Psi is therefore in gamma by the inductive hypothesis, right? Psi coming from cent N. Gamma is inductive, therefore closed under forming negations, therefore negation psi is in gamma. But negation psi is just the same thing as phi. So we're done, right? Phi is in gamma, which is what we were trying to show. Last case, phi is coming from one of the binary connective sets, right? Where this bullet could be any one of the binary connectives, and phi is coming from bullet cent N, cent N. Well, I'm not even going to argue this because the argument is essentially, only minor changes from the argument that we just gave for the negation case. So I take it that the proof by cases is complete, and so recall where we were in this proof by cases. We were trying to show that phi is in gamma, and we just ran through every possible choice of what phi is, where it comes from anyway. And in every case, it turned out that phi was in gamma, therefore phi must be in gamma, full stop. And that's what we were trying to prove, right? Because That concludes the proof by induction. So we now know that cent n is a subset of gamma no matter what choice of n, right, by the proof by induction. Therefore, right, it follows pretty trivially that cent L is a subset of gamma. And I've, right, to emphasize, I have only proved the left is a subset of the right direction, so in the next slide I'll do the other direction. To prove it in the other direction, right, if you tried to do this through an element chasing argument, you'd probably find that it's quite hard, and in the end that, you know, is because there's a better way to do this, I guess, in a sense. And again, this kind of, right, the way that we approach this is really aided by thinking about that intersection. Somewhat intuitively, when you want to show that some intersection is a subset of something, it would be great if you could show that one of the sets is one of the sets being intersected. That is to say, we would love to, right, it would be nice if we could show that cent L just is one of those gammas. Because if it is one of those gammas, then when you take that and you're also intersecting other things, those other intersections could only potentially make the set smaller. That is to say, if we can show that cent L is one of the elements of one of the gammas, then this subset relation holds immediately. So that's what we're going to do, right? We're going to try to show that cent L is one of these gammas. That is to say, we are going to show that cent L is inductive for cent 0. It's a fairly simple proof when you approach it that way. The first condition we want to check is that cent 0 is a subset of cent n, but we know that because cent 0 is, right, in the definition of cent L as the union over all cent n, cent 0 is one of the sets in the union, and therefore it's a subset. So that's easy. Yeah, in fact, I think I gave here in the write-up an argument that is even more complicated than it needs to be, right? The one that I just said verbally is maybe better than the one I wrote. Anyway, so right, so to prove that cent L is inductive for cent 0, we've proved the first condition, that cent 0 is a subset. We now need to prove that it's closed under the formation of all the connectives as the other condition for being inductive for a set. So we start with negation, right? We'll prove closure under negation. Why is it closed under negation? We'll take phi to be any element of cent L, then by definition, as a union over all cent n, phi must be in some cent n for some non-negative integer n. Well, because phi is in cent n, then by definition of cent n plus 1, negation phi is in cent n plus 1. And that, right, because cent L is the union over all of the cent n's, cent n plus 1 is a subset of that. And so we have, right, so long story short, negation phi is an element of cent L, just as we had hoped to prove, and that shows closure under negation. Again, the argument for the binary connectives is so similar to the negation argument that I'll sort of leave it to you to make the small tweaks that finish the proof. And that's it. So we have, right, we've completed, right, we've introduced this idea and we've completed our first theorem. So in the next video, we'll see how this theorem is actually one of the most important theorems, in a sense, for everything that we do in propositional logic and beyond, because it is what justifies the use of structural proofs by induction.